Hello everybody, in this lecture we will be solving 1990 IMO problem number 1. Here is a view of this problem. Chords AB and CD of a circle intersect at a point E, as you can see on my drawing here. And point E is inside the circle. M is an interior point of segment EB. And then we go ahead and draw the circle, the circumcircle of triangle DEM, and I represented it here with the lowercase omega. The uppercase omega is simply the original circle ABCD. Okay, then we are told to draw a tangent line to that second circle, little omega, at point E, tangent to that circle, and then this tangent will hit the chords BC at F and AC at G. And then given that the ratio AM to AB is T, we need to express EG to EF in terms of T as well. We need to first convince ourselves about the exact locations of those points F and G. Let's start with the point F first. So I claim that point F is located inside segment in the interior of segment BC for a very simple reason. When you consider circle little omega here, you realize that it enters into the angle BEC. As such, the tangent to that circle will hit the interior of the line segment BC. I think that's clear. Now the second one, the location of G, is a little bit trickier. So I will establish it by comparing two angles. Let's start with angle BEF. So angle BEF, when we realize because of the tangency is equal to M, well, before that, let's say BF is equal to MEF, angle MEF, and because of the tangency, angle MEF is simply equal to MDE, angle MDE. But angle MDE is less than angle BDE, and angle BDE is the same as angle BDC, but finally angle BDC is nothing but angle BAC because they subtend the same arc, minor arc BC. So therefore, so we established that angle BEF is less than angle BAC. That implies that the intersection of the tangency at point E to the circle little omega will hit AC on the ray CA beyond A. So that therefore the configuration, the correct configuration of the picture is as I showed here in my drawing. So F is inside BC, so F is inside segment line segment BC, if you will, versus G is on the ray CA beyond A. Okay, so once we establish the proper configuration of the picture, now we can do some angle chasing and conclude the problem pretty quickly actually. So let's start the angle chasing with angle CEF. So angle CEF, so let me let's use I guess the green color is fine, so let's use the green color. Angle CEF is simply equal to angle DEG by vertical angles, and this is the same as angle, so angle DEG by the tangency here, it is equal to angle EMD, angle EMD, and angle EMD is the same thing as angle AMD, which is equal to angle AMD. D. Okay. Secondly, so let's call this result as number 1. Yeah, that's number 1. Number 2, consider the following. Angle CEG, so that would be 180 minus angle CEF, right? 180 degrees minus angle CEF, and that's the same thing from the result number 1. This is the same as 180 minus angle AMD, as I said from result 1, but 180 degrees minus angle AMD is nothing but angle BMD. So that's equal to angle BMD. Now the third observation, angle yeah, let's start with angle MAD this time. Angle MAD, let's decorate it as well. Yeah, so let's say like this. So angle MAD is equal to angle BAD, obviously, and that in turn is equal to angle BCD, because they subtend the same arc on capital omega, right? Arc BD basically. So that's the same thing as angle BCD, and angle BCD in turn is just the same thing as ECF, is equal to angle ECF. So as a result, so we have that is equal to this angle over here. Finally, last observation would be angle MBD. MBD is simply equal to that 1, 2, let's say 3. Angle MBD is the same thing as ABD. Angle ABD, and that's the same thing as angle ACD, right? Let's just decorate it, I guess. Oops. 1, 2, 3. The same thing as angle ACD, and ACD is the same thing as ECG. Yes. Angle ECG. Now we can conclude. If I combine result 1 and 3, that would imply that so from result 1 we know that CEF is equal to AMD, so that's also the same decoration here. And then also from result 3 we know that MAD is equal to ECF. This implies immediately that triangles MAD and triangle ECF are actually similar triangles. In a similar way, by combining 2 and 4, I would answer CEG, that obtuse triangle, or obtuse looking triangle, and BMD, okay. And if you look at result 2, MBD, MBD, and ECG, yeah. So therefore, those two triangles are also similar. MBD is similar to triangle ECG. But now we can use length relationships. For instance, the question is deliberately asking for EG over EF. EG over EF, I can rewrite it as EG over MD times MD over EF, but then EG over MD, so EG over MD from the second similar set of similar triangles is the same thing as EC over MB. So I can replace it with EC over MB times, and MD over EF, MD over EF is the same thing as MA over EC, MA over EC, and that's simply equal to, because the EC's cancel out, MA over MB, and that's equal to Going back to the given in the problem, notice that AM over AB is equal to T, implying that AM is simply equal to T times AB. T times AB. So therefore, AM can be replaced with T times AB. In a similar way, MB let's write it here. You can easily see in the picture that MB is simply equal to AB minus AM, but we just established that AM is T times AB, so therefore this is AB minus T times AB, which is 1 minus T, factoring out the AB, 1 minus T AB, so therefore plugging it in here, 1 minus T times AB, we come up with the final result, T over 1 minus T, and this is the expression for EG over EF in terms of T, and we are done.